All right, today this is an expert mode power hour. I want to thank you all for joining us. Today we're going to be doing or talking advanced IEC 61850. This is about a 2-hour and 40 minutes, whatever it takes there, webinar going into some great details into 61850. Bruce, next slide. It will be given by Bruce Muschelitz. He's our technical senior staff consultant and subject matter expert when it comes to IEC 61850, among other things. So a wealth of knowledge today with Bruce, so we hope you get a lot out of this one. Next slide. As usual, Power Hour t-shirts will be giving out. I'm probably going to get out a few more than 3 this time. This is a long webinar, so may give out 5 or 6 shirts this time. So we'll basically look at the most engaged individuals and take the top. What I'm going to do today is probably take the top 6 most engaged, and we'll be contacting you. If you want a shirt, then we'll just need a size and a shipping address, and we will ship you out these Power Hour t-shirts. Next slide. And with that, I'm going to turn it over to Bruce. And aside, as you know, most of you, and if you don't know, if you have a question during the webinar, in your GoToWebinar pane control panel, there is a questions area. Just type in your question. We will try to answer it either live or, Bruce may answer it, or we'll respond with a written answer. And all questions and answers, if yours doesn't get answered live, will be provided in a follow-up email that usually comes out about a week after the session. So you'll see all the questions that were asked, all the answers. That way everybody that attended has that information. With that, Bruce, it's all yours.
Great. So I just want to reiterate, ask questions as you will. There are no stupid questions, only stupid answers, which we may give you, but please ask the questions. We'll do our best to come up with some more intelligent answers. So I have the agenda up on the screen. It's going to be fairly simple for the topics. First of all, we're going to figure out why 61850 is so great. What does it do that other things can't do? We'll from there branch on to what did 61850 steal from other protocols? 61850 is not a new protocol. It's basically stolen from other protocols and just applications. But 61850, the third bullet here, did add some more things. Basically, it just found a way to apply different object names. Next bullet here, we'll talk about the action services. That's the verbs of 61850, read, write, control, essentially, something like that. The next one is the modeling services. What can 61850 define? What are the nouns of 61850? Does it talk about breakers? Does it talk about voltage? Things like that. Then we'll go into a 61850 networking overview. This will be fairly brief because we plan to have a full expert mode session on 61850 networking, actually networking in general with 61850 just sort of thrown in on the side. Next thing we have is the seven data transfer methods. 61850 has a lot of ways of transferring data. There's a couple of easy ones, read and write, but there's some other ones that are more like DNP or Modbus. And the last one is we'll go into a little bit of detail on how to debug the systems using Wireshark. Now again, if you look a few notches up here, you'll see that 61850 simply stole from other protocols. That's the great part of stealing from protocols. That means that existing tools like Wireshark already understand what you're doing without having to be custom programmed. So that's it for the agenda. It's going to be fairly short. We're going to run a full, at least hour and a half, possibly more. We'll see how it goes. So the first thing we've got to get down is our terminology. There's a lot of people confused about what 61850 terminology means, and they get very much wrapped around the axle trying to figure out what are you talking about. So we're going to just go in the basic terminology and make sure we're all on the same page. It's really not that hard. The first one that everyone talks about is SCL, System Configuration Language. This is simply a file format to describe what the devices can do and what the system can do with the devices. It's just a simple format. It uses XML, which is similar to your HTML that's used for your web pages. The definition of services. Services is the actions that a protocol can do. For example, it can read the capabilities of a device. It can read files. It can write different data objects. It can control things. Those are the things that we call services. The next one is the complicated one, objects. Everyone likes to talk about their protocol or their system being object-oriented. Don't get confused. It's really simple. An object is simply a name of something. What kind of things can we name in 61850? Well, there's a lot of things that can be named. We can go all the way up to what is the name of our server, for example, with an IP address, that's the name of the server. Or we can go all the way down to a voltage or even a portion of a voltage on a three-phase system and work our way down to there. So there's a range of objects we can talk about. So an object is not something fancy. It's just a thing. In DNP, when we talk about objects, we talk about things like analog input 5. That's an object. Okay, so don't get too hung up on what this thing about object-oriented in 61850. It's just a way to name things. The next one, client. This is the device that needs the data. In DNP, we call these masters. That may not last very long based on the sensitivity of some people. They may be renaming those. So the server, on the contrary, is the other side. It's the device that has the data that the client wants. In DNP, this used to be called a slave, and it's still called a slave in Modbus, but nowadays, because of the sensitivity, we call it an outstation. It's simply the device that has the data that you want. When you see client server, what that is that's just a simple request response protocol. In DNP, that's a DNP asking for analog input 5, and the server then responds, here's your data. Simple client server protocols. The next one is publisher subscriber. This gets a little bit more interesting. Here, the subscriber says, here's the kind of thing I want to hear about, and the publisher just sends that stuff without any further request for the information. So it just sends the data to these subscribers that indicate intent to hear things. The interesting thing in subscriber publisher is that the publishers often don't know who's listening. He just sends the stuff into the air and hopes that whoever wants to hear it has gotten it. They usually do get it. The next topic is reporting. What is reporting? This is the sending of useful information without an explicit request. What happens is that the person who wants to see some data sets up some objects in 61850, and then from there on, 61850 devices evaluate what's going on in their system, and when something interesting happens that's defined as interesting by the client, the device sends messages across the wire. The reports that they talk about are not PDF reports; they're binary reports. You can't actually look at them using a visual ASCII editor. You need to use some kind of other thing like Wireshark to see these. Goose is a fast way of performing reporting, and it's reliable, and it's usually done to servers, whereas the one above it, reporting, is usually done to a client. So reporting is basically client-server. Goose is basically server-server. The last one is the most interesting to me is MMS. This is Manufacturing Messaging Services. This was invented back in the 80s by General Motors to automate their robot systems so that they could quickly switch from one model year to another. They found out that it was very difficult to have all of these robots and programmable controllers that all spoke different languages. So they invented a language for programmable controllers and automation in general called MMS. 61850 steals heavily from MMS, as does the protocol that we talked about at the last Power Hour, which was the ICCP. That also uses the exact same protocol MMS. So what's so special about 61850? Why would you possibly want to use it? We've already got our Modbus. We've already got our DNP. Why would we want to switch over to 61850? Well, the key is that 61850, first of all, it's not a protocol. It's a way of thinking about automation. When we talk about automation, that's how you want to operate a system remotely. It's to get the guy out away from in front of the screen at the local area and make that system work autonomously. Now in 61850, most people are concentrating on different pieces of it. Again, it's not a protocol. The first piece that people concentrate on is the configuration language, SCL, which we've defined before in the list of terminology. That allows you to configure the individual devices and allows you to configure the system. The advantage of having something like SCL is you've got one viewpoint of the entire system, so that you could, in theory, make for example, a single line diagram. You could generate all the documentation. You could do what-if calculations. You can calculate information data rates, things like that, all from a single source. You don't have to go back to multiple spreadsheets, multiple languages in order to get that. The second thing that people concentrate on in 61850 is the services and object models. And again, we talked about this. It's just the nouns and the verbs of the language. Reading a voltage. That's verb is the read, voltage is the noun. Simple standard object-oriented material. The next thing we talk about is the mapping of the protocol to MMS. Interestingly enough, 61850 is defined in very abstract terms, not in terms of MMS. It turns out that the only way to really implement 61850 well is to use MMS, but it's not defined that way. It's defined in very abstract terms, so you don't have to worry about the intricacies of this protocol called MMS when you're talking about 61850. The next thing we should be looking at in 61850 is things we're not going to be discussing today, is the project management. How does 61850 has a well-defined how to build a system and how to verify that system that you built is actually going to meet your needs. There's an entire part of 61850 with project management that people generally ignore because it's just not part of the protocol. Again, it's not 61850 is not a protocol. One of the important things in that 61850 brought to the table is this thing called data modeling. How do we hierarchically name things in the real world? Now, you're probably going to say that, oh, that's just a 61850 thing. No, 61850 is now infecting the rest of the world with this idea of data modeling, where they define at very high levels what this thing is they're talking about, and then they can expand that into more and more detail. And again, the reason for doing that is to have a clean way of talking about things. The last part of 61850, again, that we won't talk about, but it should be considered, is the use of third-party tools. 61850 generally is going to require you to use some third-party tools, especially to manipulate the system configuration language files and to inspect the data. Data inspection is actually going to be fairly simple. We'll see that with Wireshark, but the SCL manipulation can get a little dicey without having tools. If you want to, and you're crazy enough, you could actually manipulate SCL with some ASCII editors such as Windows Notepad. Please, please don't do that. It's very dangerous, but it could be done in a pinch. If you want to simply change the name of something, you could actually go in and change that, but please don't do much more than just changing the name of it, changing a simple name. Philosophy behind 61850. In 61850, the general idea is to move the intelligence toward the server. Take it away from the client, in other words, away from in DNP, that would be take it away from the master and push all that intelligence toward the server. The server knows when interesting data is occurring. It shouldn't be up to the person who needs the data to figure out, to determine how often to check the server for the data. It should be up to the server to figure out how often the client needs that data and to only send the data when it's useful. This is the difference between data transfer and information transfer. 61850 transfers information, whereas a lot of protocols such as Modbus, you simply do a poll and you get the same bits again and again and again, and it's up to the requester to figure out what is new. In 61850, whenever you get information across the wire, it's generally going to be new stuff that you're interested in. You don't have to filter out all the fluff that's being sent. The next part of the next philosophy behind 61850 is a name is a name is a name. When it starts at the data source at the server, the name remains the same all the way through up until the enterprise massive database. So the names don't change. In DNP, for example, you need to keep changing the name of the index in order to make sure that you don't have any collisions between devices. In 61850, the devices have a hierarchical name that makes sure that there is going to be no data collisions, so you never ever have to rename the data. You can always tell where the data came from. The next issue, and this is difficult to describe, is that we're trying to push the complexity away from the users and toward the vendors. 61850 tries to make it easy for the users, but I'll tell you from a personal viewpoint, it's a real bear for vendors to implement 61850. It really is challenging, and it's one of the more difficult things that a vendor will ever do is to implement 61850. The next thing is to enable the automatic detection of most configuration problems. In the system configuration language, for example, there is a way to detect whether that SCL file is valid or not. Most cases of the invalidity of that file can be checked. There are more tools coming online all the time. Also, if you try to put a configuration into a server, the server may complain that that's not a configuration that makes sense, and it will explain to you what has to be changed. So the automatic detection of problems. Again, the issue is that you don't want to have the problems propagate and to make things difficult somewhere else down the line. The other philosophy of 61850 is to make sure that this system configuration language was suitable for a lot of purposes other than simply configuring the client and configuring the server. They wanted to be able to use it to be able to document control flows. Where does the data start from? Where does the data go? What does the one-line system look like? What kind of data would be interesting to asset managers? For example, for a circuit breaker, you want to know how those contacts are wearing. So you can use that as an input to your asset management and allow the contact wear information to be sent to your asset management. You'll know when to do your maintenance. That's the next one is scheduled and unscheduled maintenance. 61850 tries to convert everything from unscheduled maintenance into scheduled maintenance. How do you schedule maintenance? Well, there's always two ways. One is by calendar, and the other one is by actual operation of the device. If you know the device hasn't operated, there's really no need to go and do calendar maintenance anymore. You can now selectively do maintenance on your system. 61850 enhances the ability to do this. The next one is remote operation and diagnostics. 61850 was designed to allow you to operate systems remotely. If you look at how systems have been changing, especially in the substation area, up until about 20 years ago, substations used to be manned. There used to be a person actually in the substation, and they had a heater in the substation to keep that person warm. Well, those days are long gone because utilities have gotten lean and mean about this and decided that nobody really needs to be in the substation, and you don't need to have an emergency guy there flicking the switch just in case bad things happen. This all can be done remotely and in a secure fashion. The other thing the system configuration language can do is it can simulate upgrades. So we can simply take our existing system, modify the configuration language, push that into more devices, and see how does this new system work. In general, a lot of people with 61850 have a pilot system on the side to allow you to check out new upgrades. So they have basically one of many of the devices that they have out in the field, and they use this to check out system expansions. Project management was the other part of this. It allows you to look at what it was that you wanted to put together and what you did put together. That's called the as designed and as built stages. So 61850 enhances the ability to do all of that. One moment. So, what's new in 61850? 61850 adds to existing protocols the ability to have a structured language to do everything. They have a server-centric architecture. The servers push the data to the clients after the clients set it up. What you see in 61850 is after the system starts up, there's a flurry of messages from the clients to the servers saying, here, I want you to do this, I want you to do this, I want you to do this, and then the clients get very silent and just wait for data to be pushed up from the server. And again, it's not the data, it's the useful information that gets pushed up from the server, not just bits and bytes. 61850 also allows you to do both offline configuration using the system configuration language as well as online configurations. So you can set, for example, reporting up in the SCL files, and then if you don't like what is in the SCL files, you can override them online after you start your system up using MMS. This is an important thing to do, but I'll warn you that you probably don't want to make many online configuration changes. And the reason is that if you make the online changes, you can't just look at the SCL file and know what your system is doing. If you make the online changes, then it's going to be different than what's in the SCL file, and it will become a bit more difficult to analyze what's happening in your system. 61850 also brings the server supervised controls. For example, in most protocols, you get a message is sent from the client to the server saying trip a breaker. In 61850, you don't do that. You say trip a breaker and let me know what happened. So the server then becomes responsible for verifying that the current has ceased to flow in the breaker, or that the physical contacts on the breaker have moved. It's not enough just to tell the breaker he should trip. You want to know that the breaker actually did trip. 61850 allows the server to do all that supervision, and all that comes out of the client is trip the breaker, let me know what happens. And from there on, the client doesn't have to do anything. 61850 also adds the detailed hierarchical models, and we talked about that when I talked about the names of objects, and we'll go into that in more detail later. 61850 has self-description. You can ask a device, what do you know about? What kind of verbs can you do? What kind of nouns do you know about? Do you know about voltages? Do you know about currents? Do you know about power factors? Do you know about contact closures? The individual devices can tell you that. 61850 also has extensibility, but with built-in interoperability. There are defined ways of vendor extensions of 61850 devices that are designed to be completely interoperable. Basically, what happens is the vendor makes an extension, and then the client device can ask the device online or offline, what do you know about? What can I do with you? And then it can do those operations. 61850 also added a robust time stamping system. So in the time stamping system, not only do you know what time it is, you can tell what the accuracy is. You can also tell if the clocks in the system are working. So there's a very robust time sync system, which we talked about in the generic 61850 power hour. There's also maintenance and diagnostics built in. You can tell when messages are being lost or not being lost in case you have communication outages.
Bruce,
so here's
a quick question that came
Sure.
in. If online changes are made, can you download a new SCL file from the system with all those changes? Is that?
No, that's an interesting question. 61850 was designed to do that, but most devices do not have that capability. So it has the ability to export to another source the current configuration of the device, but most devices do not implement that feature. So what you need to do after you do your experiments online of making your changes is you want to go and put all that stuff back in the SCL file and then reload the device with the modified SCL file.
Perfect.
So those
Thank
are
you very
generally
much.
temporary changes.
Okay, that's perfect. Thanks.
Comparison from DNP between DNP and Modbus. So if we think about the general time flow, systems started out with Modbus. Modbus was a fairly simple protocol that had two types in it. It had bits and it had 16-bit words. Other than that, that's all Modbus had. So you could change a bit and you could change a 16-bit value, and everything else was built on top of that in some proprietary manner. Also, Modbus only had the ability for the master device to pull the slave device. There was no bidirectional data flow. So if the master wanted to know something, the only way for him to find that out was to pull the Modbus device. As time went on, it was decided that more intelligence should be moved from the device that has the data to the device that wants the data, and that evolution took place in DNP. So DNP added some smarts to the system, and one of the smarts that it added was the ability to do dead banding and to do the ability to detect changes to inputs. So in DNP, you could ask a system, what has changed? And just send me the changes. And then you don't have to worry about polling the device for all of its information and then having the master decide what has actually changed. So in DNP, the master has to make fewer of the decisions on what has changed. Unfortunately, it still has to make some of the decisions. In 61850, they pushed that even further, where 61850 systems are designed to operate in a mode where only the new interesting data is sent from the device that has the data to the device that wants the data. There's also a few other things in here that you may want to look at. I do want to express here that DNP is not a bad protocol. Modbus is not a bad protocol, but there's just been an evolution from Modbus to DNP to 61850 to move the intelligence from the device that has the data to the device that wants the data. So that's just a general thing that you're going to see. The other important thing that you'll see is this. Can you see my cursor here? The data address. So the data address in 61850 is a named object. It's got a real name to it with character names. In the other protocols, you simply have indexes. It doesn't sound so bad until you want to add more information later on. If you add more information to an index system, some index has to move out of the way in order to add your new data, which means every time you add new data, you have the possibility of changing the name of the old data. In 61850, because they're character-based names, there is never any collision. So the old name remains the same no matter how much more you add to it. So that's a huge advantage of 61850. 61850 also adds the ability to have data structures, which DNP had little of, and Modbus had no structures. Again, in Modbus, all you had was bits and 16-bit values. DNP added a few data structures, but 61850 has a lot of them. We'll go into that later. 61850 also has timestamping, standard timestamping mechanisms of using network time protocol or precision time protocol, whereas DNP essentially standardized on sending the time within the DNP itself. And again, there were good reasons for DNP to do that, and I really don't want to go into a DNP session at this point. And again, we talked about time quality and we talked about the maintenance aspects. So 61850 protocols. Let me check how we're doing time-wise. Okay, we're sort of on time. So 61850, again, as I said before, stole from other protocols. They stole mainly from MMS, but they stole a lot of things other than MMS. One of the advantages of stealing from MMS is that was, at the time, that had all the features that were needed by a generic automation system. In fact, it had all the features that were needed by this ICCP that we talked about at the last Power Hour. So what does 61850 MMS, what does MMS have in it? Well, if you look at the last bullet here, it had built into it the associations, ability to make connections, the ability to define and use structured objects, for example, a structure of an array of floating point values, for example. It had basic built-in data types that are generally needed, 1 bit, n bit for integer, floating point values, string values in multiple lengths, structures, and other basic data types. It also has the ability to do read-write of data, which is mainly what's being done in 61850, and it has this extra thing called reporting, which is a spontaneous sending from the server to a client on an established connection. MMS also has the ability to define and use data sets. Data sets sounds like a complicated term, but it's really just a list of names treated as a single object. So it's just a list of names, nothing more to it than just a list of names. So just think of it as a list. It's not the values, it's just the names. MMS also had the ability to do self-description. You could ask a system, what objects do you know about? What services are you capable of doing? Can you do writes? Can you do reads? Can you do file writes, for example? 61850 also has a basic file system, which was a flat file structure with no directories. Now, people think this is terrible. How can you have a file system with just basic names of files? Well, you can make this work, and 61850 expanded that to make it into a hierarchical file system. In some cases, MMS needed to invent some new protocols. We'll go into that in the next slide. I'm sorry, slide after that. Other standard protocols that were used besides MMS, network time protocol and precision time protocol. I'm sure most of you have heard of this IEEE 1588. That's a very, very precise protocol. It's designed to go down to the nanosecond type level. They say it's going to be the last protocol ever needed. And concerning time, I'll wait and see if that actually occurs. Another one that 61850 stole was the parallel redundancy protocol and the high-speed ring redundancy protocol, which are at the wire level, the data link level, and it allows for what they call bumpless redundancy. In other words, if you lose a wire, you will lose absolutely no data, no matter how fast your data was being transmitted. As an interesting side note, I was at a a conference, and one of these bumpless protocols was being shown, and the way they showed it was they had the data going across two different fibers, and they allowed people to put the fiber on a piece of wood, and they allowed them to grab a hatchet and chop the fiber in real time and watch on an oscilloscope whether any data had been lost. There were a lot of people with hatchets and a lot of little pieces of fiber optic left over at the end of the day, but boy, was that a lot of fun to watch. The next one is the rapid spanning tree protocol. This is used by when you have a mesh of Ethernet devices, and you want to have some redundancy of the links, but you don't want to have to pay for it. This is actually free. It's built into a lot of Ethernet switches. Unfortunately, it takes time to cut over if you have a data loss. In an office environment, which is where it's used mainly, people don't care if it takes 50 milliseconds or 100 milliseconds to cut over. In an automation system, 50 milliseconds or 100 milliseconds could cause an enormous amount of problems in your system. That is just, again, in many automation systems, that's forever. Another thing it stole was this ASN1, Abstract Syntax Notation 1. There is no Abstract Syntax Notation 2. And basic encoding rules. This is the bit-level protocol used to define bits across the wire. You may know this as a tag length value system. So if you've ever seen other protocols used on the network that say their tag length value, also TLV is another term. These are using the ASN1 and the BER protocols. Again, stolen fair and square by 61850. 61850 also used, without change, the International Standards Organization layers 4 through 7. We'll go into what the layering is, but this is the transport, the session, the presentation, and the use and the application layers. So they stole those fair and square. The next thing they stole was things from the IETF, the Internet Engineering Task Force. Request for comment 1006, and I'm really sorry for all these numbers here, and request for comment 1240. Forget the numbers. It's just a way to interface between standard good old TCP/IP and the ISO layers used by 61850 and other upper layers. It stole Ethernet fair and square. Ethernet's the same thing we've been using at our desk for a couple of decades. Nothing new, any data rate, any encryption, any media, whatever you want to use. 61850 is quite happy with it. 61850 also stole XML, which is the basic language which is used by the internet for web services and for to transfer HTTP messaging. It's used for mail. It's used inside of Excel and Word, etc. So it's really nothing new. And the use of all these standard protocols allows you to use existing protocols such as Wireshark. So Wireshark doesn't necessarily need to know anything about 61850 in order to make good sense of it. So 61850 did add some new protocols, and you'll see the list is really short. They added this thing called Goose, which is just a repetitive way of sending a bunch of data. The bunch of data is actually a data set, which we talked about, which is just a list of data. They added controls. There are 5 kinds of controls. We'll go into this in more detail later. This is quite important. There's a status only, which is a no control, and then there's the 4 types of controls we can actually change it. Interesting enough, in 61850, controls are by definition able to read stuff in the real system, but not necessarily be able to change stuff in the real system. It's kind of odd how controls work. It's another mindset. 61850 also has the ability to do reporting. This is the ability of this is the defined capability of a server to monitor the values of a data set, list of data, and decide what's going to be important to a client based on what the client has told them. 61850 also adds this thing called buffered reporting, which allows the server to store data store a fairly small amount of data to cover when the physical connections are lost, and to be able to recover all of that data when the system is regained. Again, it's a limited amount of data that's stored. You can only have a finite amount of data storage, but it does get you over the issue of what happens if I lose a connection. Do I lose data? The answer in 61850 is no. 61850 also converts that flat file system into a hierarchical data system, basically by just putting slashes in the flat file names and pretending that they're names of folders. Windows does the same. Windows does the same thing in appearance to you. It actually shows you that if you look at File Explorer. 61850 also adds this thing called substitution, which is the ability to change the data at the source and pretend that the data is something else. This is useful when you're doing simulation. It's also useful if you've got an outage. For example, if you've got a breaker in the field and the breaker contacts have broken, and the breaker is actually in the closed position, and you want to convince the system that's actually closed, you can use the substitution system in 61850 to override the fact that the device is actually seeing the breaker is open and force it to be in the closed position. This is very useful in the automation because this device is probably sending that breaker position to another device, which will be very unhappy if he sees current flowing if he sees no current flowing in a closed breaker, for example. The last thing it adds is the sampled values, which allows you to send high-speed cyclic data. We'll get into this later. That's useful for things called merging units. And I don't want to go too much into merging units, just the fact that it's high-speed periodic data. What action services can 61850 do? 61850 has only 3 things it can do in terms of message exchanges. The first one is the obvious one, which is simple client-server, and the client makes a request to the server, and the server answers the question. Pretty darn simple. Client could say things like, what's the voltage today? And the server could say, the voltage is 121.35 volts. That makes the client quite happy. Moving off to the far right, we have publisher subscriber. This one is interesting in that the publisher configures, the subscriber says, this is the kind of thing I want to see. When something like this happens, please tell me. And then the subscriber goes silent, completely silent. The subscriber doesn't necessarily the subscriber doesn't actually tell the publisher what it's looking for. It assumes that the publisher is going to send it, and it decides which one of the published messages it's going to receive. So when the publisher sees something interesting happen, he will send these events shown towards the bottom when something interesting happens. If that event is something the subscriber is interested in, he'll receive it. If not, he'll let the event fall on the floor. So for example, we could have a subscriber that's interested in the voltage of the system, but not interested at all in the amps. So when the publisher sends events with voltages, he'll listen to those. When he sees the events with amps, he'll just ignore them. So you can see the publisher just keeps sending the stuff out, and the subscriber may or may not listen to those messages. It's up to the subscriber. The publisher, in fact, doesn't even know which subscribers are listening to individual messages. In the middle, we have something interesting, which is the enhanced security model. In this case, the client makes a request. The server responds with, I heard that request and I think it's okay. And then later on, sometime later on, the server will go and verify that that request has actually taken place, and will go and tell the client either it took place properly or something went wrong. So this is used. I talked about this before for the breaker trip system. So the client could say, trip the breaker and let me know if it tripped. So the client will send the request, trip the breaker. The server will say, the breaker seems to be in the position that will want to be tripped, and it looks like there's no interlocks which will keep me from tripping the breaker. I'll try to do it. So he'll send the response, I'll try to do it. He'll then continuously monitor the breaker to see if the breaker has actually either tripped or not. As soon as the breaker trips, he'll send a message with that called command termination saying, okay, I tripped the breaker and everything is fine. If it doesn't happen after a certain amount of time defined in the server will then send a message saying, I tried to trip the breaker, but sorry guy, I just couldn't trip it and you'll have to do something else. Typically, if it's a substation, the something else turns into a radical reconfiguration of the substation, sometimes resulting in an outage. So some service examples of what 61850 can do, and again, we have those three types that I had on the previous page. The left one is a request response, which is just do it and the server says okay. The middle one was the request response command termination, that's second from the bottom, and the bottom one is publish subscribe. So publish subscribe, it could be things like send and receive a goose. You've all heard about goose, and the goose is about the high-speed transfer of information. So the server has information, for example, it could have the position of the breaker, of all the breakers, and it could broadcast that to all the other servers, and the servers could decide between them, are all the breakers in the right position according to what I need to do. So that's the publish subscribe. We also have the request response command termination. Again, that was the breaker supervised, and I gave the example of the client tries to do the control. The server then says, "I'll try it," and then a couple hundred milliseconds later, the server will then respond, "Sorry, the breaker is stuck. You have to figure out what to do." There's also ways of setting blind controls. So you could say, just try to trip a breaker, and the response could be, okay, I'll try. Generally, it's not done, but you'll do things like this, for example, for enunciators. To turn enunciator light on, you'll just say, turn the light on. You really, really don't care if the LED is actually emitting light. Okay, all you really care about is you've tried to do it, and the vast majority of the times it will actually begin to emit light unless something really, really bad has happened and you've got more problems than you thought. So blind controls are generally used for almost everything except for super critical things like breakers. We also have the ability in 61850 to define that list of names that are used in a data set. We can look at the value at the list of names in a data set. We can look at the value of the objects behind that list of names in the data set. We can simply read simple objects. We can do a thing called configure control block. That's nothing more than writing to some objects. So you can look at this offline and see some other service examples. Other services that are used by 61850, the time sync protocol. Again, there's a couple of different time sync protocols that are used in standard 61850 devices. First one is SNTP, Simple Network Time Protocol. It also is compatible with normal network time protocol, and that gives you about a millisecond or so time accuracy over Ethernet. Is a millisecond good enough? Sometimes it's good enough, sometimes it's not good enough. It depends on your needs. Generally, it's probably good enough. The next one that we can go to is Precision Time Protocol. This requires hardware assist in order to get very accurate times. The accurate times you're talking about are up to 100 nanoseconds of time as good as 100 nanoseconds of time accuracy over Ethernet. But in reality, you're usually talking a microsecond or so of accuracy after you go through a bunch of Ethernet devices. The last one that we'll talk about is one that's not defined by 61850. It's the good old IRIG-B, which I'm sure you've used. It's good to about 10 microseconds. It's not bad. Unfortunately, it requires dedicated wires. And the dedicated wire means you need more wiring going to each of the devices. Each time you add a wire, you add another screw terminal block. Each time you add a screw terminal block, that's one more wire to get loose and cause problems. If you transfer the bulk of your information over Ethernet, there's only one Ethernet connection that either is there or not, and there's no longer any screws that can come loose in your wiring termination. Other services are
Bruce,
GSS.
real quick, sorry
Sure.
to interrupt. There's a perfect time for a question on PTP that came in.
Sure.
Does 61850 support all of the PTP profiles or just certain ones?
There are two profiles of PTP that are supported by 61850. There is the 61850-9-3, which is the one that is actually named 61850, and there's also one from the IEEE called C37.238. C37.238 is what we'll call the enhanced version of 61850 timesync. So it does not support, for example, the audiovisual one. It doesn't support the telecommunication one, but generally PTP devices will support multiple of these profiles. So if it needs to have both telecommunication and 61850, it's fairly easy to buy a time server that will broadcast both of those profiles. So
Perfect.
it's not an either or. It's you can tack multiple of these profiles together.
All right, thanks.
Sure. So the next service is the GSSC. This is a really almost completely obsolete version of the old UCA Goose. UCA is the predecessor to 61850. It's sort of similar to the way Goose works. We talked about Goose in the first of these seminars, but it can only send bit pairs and it can't send generalized data, and it's limited to the number of bit pairs. It was a good idea back in the mid 80s, but it's really gotten long in the tooth since then. I'm sorry, the mid 90s. Last one is another service is the routable Goose. This is the ability to send Goose over something that's routable with an Ethernet route. For example, 192.168.1.1 would be a route. Standard Goose and sampled values cannot be sent over an IP address, but only on a local area network. The ability to route these Gooses allows you to extend your system to beyond a small area into a larger area. The downside is it's slow. The other downside is you've probably got to put it on the public internet, which makes it then vulnerable to all these hackers. So security then becomes very important when you start talking about routable protocols. The last thing the last service is the file operations, which is the obvious file services that you've got in all kinds of devices. The ability to read or write a file, to delete a file, to get a list of files, to figure out how long a file is, things like that. Controls. This is where 61850 gets very interesting. A 61850 control has a mandatory ability to read something and the optional ability to write something. It's really the opposite of what we normally think about controls. So a control, for example, can look at the state of a breaker without having the ability to actually change it. That's a perfectly valid control. Okay. In fact, that's done quite a bit in 61850, where some devices just want to be monitors and not have the ability to control things. I mean, to actually modify them. So having the read-only access makes it really good for things to look at. For example, if you want to have an annunciator panel, you don't want to have the annunciator panel have the ability to trip a breaker. That would just be a very dangerous thing to do. So 5 kinds of controls. We have the status only. We have 2 kinds of normal controls, ability to write controls, and 2 kinds of things called enhanced. When we see the word enhanced, you'll often see the thing called it enhanced security and normal security here. Please don't get confused about security of the bits and bytes and encryption. That's not the kind of security they're talking about. The kind of security they're talking about is verifying that what you told it to do is what it actually did. That's the security part. So it's not encryption type security. It's actually just verifying that it actually happened. So 2 kinds of things we have with a thing called direct operate and select before operate. I'm sure you know both of these, but just as a brief version, in direct operate, you say do it, and the device does it. In select before operate, you say arm the system to do it, then yes, operate the armed system, and when it's done, tell me that it actually happened. So it's a two-step process on the for the client to send out, whereas the direct operate is a one-step process. Again, the one step is do it, and in select before operate, it's arm to do it and then do it. There are historical reasons for using select before operate. I don't want to go into it, but in general, select before operate is not often used in its real mode. When you see 61850 with select before operate, almost all the time, those two commands, the arm and then operate, are done milliseconds apart. There is no gap between them. So it's really not used in the historical sense of how it used to be used. It used to be a hardware interlock or even a software interlock. In fact, you'll still see some of that happening in your operator panels, where you arm the output, where you arm it, and it says, "Are you sure?" And the "Are you sure" is what causes it to actually do the operation. So that happens usually at the HMI level, the operator level, but it doesn't happen at the protocol level anymore. And I think I've talked about all of this. The two most common controls you'll see are the direct operate with normal security, which is just do it, and the enhanced security with select before operate, which is arm it, try to operate, and then let me know in a couple hundred milliseconds whether it operated or not. 61850 also has the ability for the server to go and send unsolicited data to the client. So the client sets up what it wants to see, and on that connection between the client and the server will then push the data back to the client. Now, again, I said we have a connection. So the client makes an association with the server, maintains the association, and with that maintained association, goes and tells the server what information to send it. There are two kinds of things that it can send. You can send either periodic data with a fixed time interval, or not periodic data, or the opposite. So not periodic data is typically called asynchronous data. So periodic data, one thing you can do with periodic data is you can send sampled values, which are used for merging units. And a merging unit will take the current and voltage, sample it 4,800 times per second, and then send those samples 4,800 times per second across the wire to interested devices. Non-periodic data includes goose and report. And what happens there is that the server decides what changes are interesting and sends those. In the periodic data, it just sends those on a periodic basis. Once every 4800th of a second, it's going to send a new piece of data, whether it's changed or not. In the non-periodic data, you evaluate whether it needs to go and send those. So the end device, for example, the server, could be looking thousands of times per second for changes, and then when something happens, it will then send those changes back to the client and say, I've seen a change. This is the kind of change you were looking for. There are two kinds of reports that can be sent. Oh, sorry. With the non-periodic, if you're sending reports, you have the ability to do what's called integrity period, and the integrity period is essentially a dead man's timer on reports. So even if nothing interesting has happened according to the server, it will then send a report with all of the data it could possibly send. It's essentially a fail-safe. It's not used very often, and you really don't have to send them very often, but it's sometimes used by people who've used previous protocols such as DNP. In DNP, there's something called an integrity scan, and people think that because DNP had it, they need to put it in 61850. Generally, it's not required anymore. There are two kinds of reports. There's one kind of report where the server tries to send it to the client, and just makes it what's called a best effort ability to send. And the second one is when it will make an effort to send it, and if the connection does not exist, it will just put it into memory for later sending. So the first one is called unbuffered, and that's useful when old data, stale data, is useless. There are times when stale data is useless. Think about an operator panel. You don't really care what the voltage was half an hour ago from your operator panel. You just want to know what the voltage is right now, because half an hour ago the data is completely useless. So if you lose data while your connection is down, that's not a bad thing. In fact, it's a good thing, because when your connection comes up, you don't need to see all that data that was all those voltages and currents that happened while you weren't connected. Buffered data, on the other hand, is useful when the previous values of the data are useful. Think about breaker position. If a breaker is on and you lose a connection, and when the connection gets regained, the breaker is on, it's kind of important to know that the breaker went off and back on again while the connection was lost. So in that case, the historical information is useful, and you'd want to use buffered reporting. So a lot of people think that buffered reporting is just always better than unbuffered reporting. That's not the case. You need to think about, is the value of stale data, is it useless or useful? Data transport service 61850 sends data across the internet in 3 different ways, and only 3 ways. One is sending it across what's called layer 2, and this is used to send it at the lowest level of Ethernet that's possible in order to maximize the speed of data transmission. That's used for the goose and the sample and sampled values. So the goose was the aperiodic sending, and the sampled value was the periodic sending. The next one is UDP-IP. This is used by network time sync, and it's also used by the routable goose and sampled value protocols. And again, I talked before about that. Routable sampled value and goose protocols are very useful if you want to send things far away, for example, across the continent or across the state, and you want to do that between 2 different servers. That's what it's useful for. The downside is it's slower, and it brings to mind all that security baggage that you have to add to make sure that anybody can't listen in and alter the messages as they flow. It's basically quite complicated to add in all that security. TCP/IP is used by 61850 for everything except for the publish subscribe, the goose and sampled values, and the time sync protocol. So TCP, if you're familiar with how TCP works, they call that a reliable protocol, and or in other words, another term is guaranteed delivery. Well, you don't always need guaranteed delivery. If you make a request for something, and that's something, and you get no response saying that I heard that request, generally you kind of know that the delivery didn't happen, and you'll simply ask the question again. This is what happens in NTP for the time sync. If you request the time and you don't get an answer, you'll just ask again later on, what time is it now? And it really doesn't matter too much that you've lost that request for that request. TCP though is more reliable, and so that if the one end sends the data, the other end is guaranteed, almost guaranteed, to actually receive the data. And you kind of see that thing on your PC when you go to a web page, and the system starts getting really slow, and you say, my gosh, the system's getting slow. Well, what's happening is this TCP is trying to guarantee that it's sending the data that was sent by the web server. It may take a while, it may take minutes, but it's definitely going to get there. Sometimes taking all that time isn't very useful. Sometimes by the time you get the data, it's stale. That's the real reason that NTP uses the UDP protocol, because the data that was sent a few minutes ago is not useful anymore. If it doesn't get the response within a second, sorry, you just can't do anything with the data. You've got to throw it away and make a new request later on. Now, we say that the protocols for non-TCP are unreliable. This is, sorry, before I said with the unbuffered reports, it sends a report, and if it doesn't get there, it will do the next report later. This is not actually true because the reports are sent over TCP. TCP does its best to get reliability in the system. As long as the connection does not get dropped, TCP will do its best to get the message across. So unbuffered reports are generally going to get across, even though it's at the MMS level they're termed unreliable. So that makes, I hope that makes sense. But unbuffered reports are more reliable than they sound. They almost always work. For NTP and Goose messages, they don't have that guaranteed delivery, and they in those protocols themselves, they have their own reliability mechanism. In NTP, we just send the request again at a couple of seconds later, and in Goose, it's done in a different way, which we won't go into exactly how that's done, but it does have a reliability mechanism. So I'm going to take a short coffee break. What can 61850 describe? Data models. This is a very busy slide, and I apologize in advance for the busyness of it. Checking my time again. So 61850 defines a very hierarchical system. At the very top of the hierarchy is the server. What's a server? That's the kind of thing with an IP address. It's pretty simple. So, for example, you could have something at 192.168.1.1. That would be a server. In 61850, you use the TCP/IP protocol using port 102 to talk to 61850 devices. If you're not familiar with the ports, you will recognize at some point that HTTP, the web stuff, uses port 80. Mail uses port 23. Timesync uses port 123, but these are all well-defined ports. So 61850 talks across using the IP address plus the port number 102, and that gets you into the server. Inside the server has multiple things called logical devices. A logical device is simply another grouping of data. I don't want to go into exactly why you'd want to do that. Inside the logical device, again, you get multiple of those. We have a multitude of these things called logical nodes. What's the logical node? It's another grouping of data. Inside of that, you've got this green box that I've shown, that inside the logical node, which is called the data. This is a list of things that are inside the logical node. The logical node in 61850 is defined to be, not always true by the way, defined to be the smallest amount of group of data that makes sense. Okay? It's supposed to be a small amount of data, 5 or 6 things, for example. You're supposed to use multiple ones of these logical nodes together to make a function. For example, in the electrical power industry, we've got a thing called directional relays, and directional relay will look for overcurrents going from left to right or right to left. So in order to distinguish between the left to right and right to left, there's a direction logical node that says what is it flowing left to right or right to left, and another logical node that says what's the value of the current. So both of those logical nodes put together make up the function called directional overcurrent. So the data inside the logical node is then grouped into a data set. Now it's not obvious from this, but a data set can contain data from any logical node. Okay, so you take a data set contains data from multiple logical nodes. That data set is used, again, remember data set is just a list of names. It's used for reporting. It's also used for this thing called logging, which we went into on the first session. And logging is just like reporting, except it doesn't send it across the wire until the client requests it. The data set is also used in the Goose to define what it's going to be monitoring for changes. and it's also used to define what in the sampled values. For example, an emerging unit, the old one called 9-2 LE is defined to have 4 volts and 4 current measurements, so the data set consists of 8 items, 4 volts, 4 currents, and those are sent every 4,800 times per second in the SMV service. So on the right-hand side, you'll see the services that are used for these different things. The data also has the ability to modify other things, and we went into these before in the first session, setting groups, substitution. We also have the ability for data to do the controls, which I've talked about. We have the ability to get and set. What is get and set? That's read and write the data. We also have the ability to get a directory of the data. What's directory? That's simply what data do you have? It's very simple. What do you got? So you can say what data do you have inside of this logical node? What logical nodes do you have inside of this logical device? What logical devices do you have inside of this server? And again, it's all hierarchical. You can also say what is contained inside this data object. For example, one of the data objects could be a breaker position. A breaker position is not just a position. It's also got, for example, the timestamp, the quality of that position, whether it's been substituted, and a bunch of some definitions, some descriptions. It's got a bunch of things attached to it. We'll go over that in a second. But the data at this level here is simply the data at the logical node level. Again, usually you have 4 or 5 different things there. Now, drilling into the data here is where it gets more interesting. So starting at this logical node, starting at this green box, okay, a logical node, again, it's the smallest amount of data that makes sense. 61850 defines 300 plus number of logical nodes with these data objects. The logical node, there are special logical nodes to identify special characteristics, for example, that define the physical device and define the status of the logical devices. The first letter of the logical node defines its type. For example, M logical nodes define measurements. P logical nodes define protection. Logical node names have exactly 4 characters, always 4 characters, where the first one is defined by the type and the last 3 are defined by what it is. For example, you have a logical node called PTOC, protection, time over current. Time over current means that it's acting like a slow blow fuse. Okay, so it takes more. If there's a small amount of current, it takes more time to trip the breaker, and a large amount of current takes less time to trip the breaker. So that's an example of a logical node. Another logical node would be MMXU, which is the measurement unit. So it's a 3-phase measurement unit. We also have MMXN, which is a single-phase measurement unit. Again, starts with M, so it's a measurement. A data object is embedded within these logical nodes. I talked about it. There's just a few of those inside of the logical node, and it's supposed to represent a thing. And for a measurement, a thing could be an ammeter. An ammeter, that's something with 1 needle on it or 3 needles. It depends. It could in a MMXU, it's an ammeter with 3 needles, 1 per phase. In an MMXN, it's an ammeter with 1 needle, because it only has a single phase. Each of these data objects has a definite type, which is called a common data class. There are 40 different common data classes within 61850. Again, it's a limited number of these types of objects. And inside of these common data classes, there are again things called attributes, which are usually the simple stuff inside of it. So, for example, we have a common data class for an object that can represent the on-off value of a lamp. So, on-off value of a lamp. Why is that so special? Well, I might want to know is there a way to control that value? What's the timestamp? When was the last time that transition from on to off? Is the quality of that something I can trust? Things like that. So these get quite complicated in terms of how they're structured. Here's an example of an MMXU. MMXU contains multiple data objects, each of them of the type. One of them I talked about was an ammeter. I'll talk about two other things that could be in there. One of them is a total watt meter. So it's a single needle that shows you how many watts are flowing on that power line. That's the green one. On the bottom, we have a three-phase watt meter. It's got three needles on it. Okay, it's got a needle for phase A, a needle for phase B, a needle for phase C, and I've shown on the bottom here a needle for the neutral phase, which is kind of an interesting concept in 61850. So you can see the breakdown of this. So the data objects are called W, total watts, and W for watts. Those data objects, the type of data object for total watts is called MV. That's the common data class for total watts. The common data class for total watts for measured value has the instantaneous magnitude, which is the non-deadbanded version, a magnitude, which is the deadbanded version, a quality, a timestamp, a deadband for how much it should change before you report it, and a description. That's a small number of the kind of things that you can see in MV. There are other optional stuff. In the three-phase object called W, it's a common data class called Y. That's what they call a polyphase with neutral measurement. It has in sub objects for the multiple phases of it. For example, phase A, phase B, phase C, neutral phase, the net phase, etc. And inside of each of those, we have what's called an analog value. What's an analog value? Well, an analog value consists of a vector called in this particular case, we have the deadbanded vector, which has both a magnitude and an angle. Because remember, we can have the phase angle of a three-phase system for multiple phases. We have quality and timestamp and deadbands and descriptions, all of that for phase A, and then a duplicate of that for phase B, a duplicate for phase C, and these things get very long. You'll see that I have for vector, I wrote down mag.f. That's not quite true. Mag is actually this thing called if you look up, you'll see the analog value for mag above. So an analog value consists of a sub-value for float, another sub-value which I didn't bother showing for an integer value. So magnitude can have an magnitude could have an analog value can have an integer or a float attached to it. A vector contains a different, it's kind of confusing, a magnitude and an angle, but a different kind of magnitude. So basically the structure of the vector is the same on the magnitude part of the vector is the same as the structure of the inst mag in the green part above. I know that's a little unclear, sorry about that. If you look at this diagram offline, I think it'll make it quite a bit more sense. Other types of 61850 objects, again, we talked about these. They're fairly simple. The one is called a data set, just a list of object names. Again, don't read anything more into it other than it's just a list of names. The next thing is the control block. The control block is simply a defined group of things that make sense. For example, we have what we call the goose control block. Again, remember the goose is the high-speed data transfer mechanism from server to server. So what would we want to know for a goose? Well, we want to know is it enabled? That's the attribute here you'll see for goose enabled. We'll also want to know how we're going to name that when we send the value across the wire so they can see it. That's the goose ID. We'll also want to know the data set. What is being transferred in that goose so that both ends can properly understand what it is. So all of that stuff is contained within the group of objects called a goose control block. We have similar things for the unbuffered report control block to define how to do unbuffered reporting, another one for buffer reporting, another one for sampled values, another one for setting groups, another one for setting up what they call logs. There's just a lot of these things called control blocks. But again, they're just lists of simple types that are defined in a certain order and certain values in order to make sense of what's going on in these things behind it. 7 ways to transfer data. This is unfortunately a simplified version of it, and I hope you don't try to read all the words here because it's difficult to follow. There are 7 ways to send data from a device that has the data to the device that wants to have the data. The one is that the client polls the object. So he says, what's the current value of voltage? And if you look on the first column here, is the receiver, the client, guaranteed to have the most recent data? And the answer is no. Because if he only looks at the server once per second, the server can have changed the values somewhere between the time that it looks. So it's not guaranteed to have the most recent data. Can it lose the changes? Yes, if you don't look at it often enough, you will lose those changes. Can multiple clients receive the same information? I wrote down no. And the reason is because if you've got 2 clients asking the same server for the values, they're really 2 different values that it's looking at. So the first client could be looking once a second. The second client could be looking once every 10 seconds. And they'll really get different, they really can have different values. They won't have the same information. A typical client for that would be a browser, for example. Some device goes and an engineering laptop wants to know what's the current voltage. We can look at the other ones here for unbuffered reporting. In unbuffered reporting, the server then decides when to send the data. So the receiver, in this case the client, is always guaranteed to have the most recent data. Because whenever something happens that the client's interested in, the server will have sent it again. It also is guaranteed to send all of the changes. And you can look through the rest of this, and I really don't want to go through every cell of every column, but the other ones are buffer reporting, and again, we talked about the buffer reporting. If you lose the connection, or it will remember it. When you regain the connection, there's a mechanism for the client to go and say, I know the last one I saw was 5 minutes ago. What did you have happening since that 5 minute ago time period? And the server will then respond with all of that information. There's also the goose, which is the server-to-server data, the sampled values, which is for a merging unit to a device, typically a server. When I say sampled values, this is typically used by protective relays to get data from the substation. There's also logging, which I talked about a moment ago, which is the same as reporting, except instead of the data being transferred across the wire, it's just like buffered reporting that the connection's always lost. Okay, so the data is always remembered and never sent across the wire, and the client can say, what was that data value that was 5 minutes ago? I want to see it again. So it can read the data from 5 minutes ago to 1 minute ago, for example, give you the range of data. And that's useful for things like what was the historical value of the temperature of a certain device. You may want to see that. So you just log those. You really aren't interested, you're not interested in the temperature until something goes wrong, and then you want to know what the temperature was half an hour ago. So that's what the logging is useful for. We also have the file transfer, which is generalized files. One of the bad things is that the file formats in 61850 are not defined. So you can send, so the good news is you can send any kind of file you want. The bad news is they're not defined. What they do define is the ability to send ComTrade files back and forth. They do define a ComTrade file format. In fact, they define a zipped version of the ComTrade files, so you can send a zipped version ComTrade if needed. All right, quickly, networking overview. And I hate to do this, but this is the obligatory 7-layer OSI model. They showed the same model in the ICCP Power Hour in the previous one, so I need to show it again on mine. There's a lot of stuff, and it's a very busy slide. On the left-hand side, we can see what the layers are called. So we've got L1 through L7. Those are the multiple layers. Everyone who wants to claim they're a network engineer has to have memorized all of these layers and exactly what they do. People who use it don't have to memorize any of this stuff. What you need to know is that as you go up in the layers towards the top, they get more and more complex, and you add more information to it. Specifically, if you look on the far right, you add addressing information. So let's work on the addressing information so you understand how things are addressed. At the physical layer, the addressing is the connector. For example, you've got the address could be hook up to fiber number 1 on my device. That's a physical address. Okay. At the Ethernet layer, you have what's called a MAC address, Media Access Control address. This one is typically hidden because there's a way to automatically discover these. It is used, however, for things like goose and sampled values because again they're transferring the data directly. If you look on the left-hand side of the diagram here, the sampled value and goose are being transferred directly on the Ethernet and requires a MAC address. Normal transmissions, everything else except for goose and sampled values, are transferred using Internet Protocol. An Internet Protocol address looks like 10.0.0.1, 192.168.1.1. Those are kind of IP addresses. There is a way in TCP/IP for a device, if it knows the IP address, to find out what this MAC address is, if it knows the IP address. Since sample value and goose don't have an IP address, there's no way to discover that except by knowing explicitly what this value is. The MAC address is typically tied to the particular receiving device. In fact, the MAC address is what they call globally unique. There is nobody else in the world who will have the MAC address 00D04F123456. That is guaranteed to be unique ever in the world. There cannot be any duplicates of that. Whereas IP addresses can be duplicated because I'm sure everyone has a 10 dot address who's listening to this on the call. And those addresses are not guaranteed to be globally unique. Above that, we have the address of the protocol. For example, for UDP, we have an address of 123, which is defined as the address of the timesync protocol. In the TCP world, we have an address of 102, which is defined as the entry point into the upper layer addresses. Specifically, this thing called RFC 1006 is actually the thing at TCP port 102. TCP port of 23 is mail. TCP port of 80 would be HTTP, which is your normal web browser. And there's a bunch of other standard TCP ports. Generally, you don't need to know these. You just need to know that they're well defined and used. Above this, we have the ISO layers, which are used by 61850. Each of the layers in ISO also require these things called addressings. So the transport layer these addressings are typically called selectors. Okay, instead of calling them ports, we call them selectors in the ISO world. So we need a transport selector, a session selector, a presentation selector, and the selectors in the ISO world are pairs of digits, and in a number of pairs of digits. Once we get beyond these layers here, we then have to get into the addressing of the MMS layer. The addressing of the MMS layer, it turns out, is optional. But an addressing for an MMS layer will look something like 1399991. this would be an example of an MMS layer. You can also put some additional information for the layering called an AE qualifier. You'll very rarely see any of this. Generally, it just sort of works, and all this stuff is built into 61850. So whenever you get a device, all these things are defined, and you'll see all of this sometimes, especially these selectors here. You'll see them defined for your device, and it will tell you what selectors to use that will make the device work. Essentially, all automatic. That's pretty much all you need to get from this, other than the fact that the IEC, the International Standards, the International Electrotechnical Commission, the International Standards Organization, and the Internet Engineering Task Force have all cooperated on defining these. And also, it's unclear here, but the Ethernet is actually defined by the IEEE, the Institute of Electrical and Electronic Engineers. So why is the addressing important? The addressing is important because each layer needs to know where to send the data for the next one. And the addressing is required in order to make things work. Sometimes it's just implicit in the protocols that are used. For example, when you talk an HTTP protocol, you can pretty much be assured that you're talking port 80. It will automatically translate that into port 80 unless you tell it to use something else, and you can tell it to use something else in certain circumstances. Ethernet switches operate at layer 2, and Ethernet routers operate at layer 3. You'll hear these terms later on, and we'll go into a webinar later on networking, which will discuss what a router and a Ethernet switch is. For example, the Goose is at layer 2, and I did explain this a bit. So it uses the MAC address. It never has. There's no such thing as an IP address for a Goose. Let's go back and look at that. The Goose talks directly to the Ethernet layer. It goes through this thing called EtherType and talks to the Ethernet layer. It doesn't talk to the IP. It never has an IP address. So if somebody says, what's the IP address of your Goose? You just have to tell them, I have no idea what you're talking about. That's not even a question you can ask. The layering is there to allow you to substitute layers. For example, you can just replace that IP layer with a secure IP layer, and nothing else above it or below it has to change. This is useful in order to have a well-defined system that you don't need to talk end to end about all the different layers in between. You can simply replace one layer in the middle and not have to change anything else, and everything just continues to work. As I said before, most of the time you can just worry about you can just have the default values unless it's under very, very special circumstances. Some devices in addressing hide the data. Now, this is a very important thing to remember. For example, a router will never, ever, ever forward layer 2 traffic. So if you have data on layer 2 that is not put on a higher layer, it will never be forwarded by a router. For example, if I have a Goose that's sent on layer 2, the Gooses can never, ever go through a route, can never escape the router, which is a good thing because on the other side of the router, you probably have something like the internet, and you certainly don't want to be putting all of your data on the internet because unfortunately then they can send their data back down to you. Another thing to remember is that Ethernet switches will selectively forward layer 2 data by address. I don't want to go into too much of that, but basically it minimizes the amount of data that's being transferred by an Ethernet switch, and it can surprise you by obscuring data while you're debugging it. I've been surprised many times when I'm trying to look at 61850 data or DNP data for that matter, because an Ethernet switch is hiding the data from me, because it's supposed to hide the data. This is the difference between, if you remember this, between an Ethernet switch and an Ethernet hub. By the way, if you ever get a chance to buy an Ethernet hub, I would suggest buying it now because they're becoming very difficult to get, and they're very useful. So how to debug with Wireshark? First of all, as I said before, our Ethernet switches here, a standard Ethernet switch, hides the data. For example, if the client is talking to the rest of the system here, okay, the data will go into the switch and come out to the remainder of the system, and the server will never see that data. The PC will never see that data. It's being hidden from devices that aren't concerned with that information flow. And the switches do that for you automatically. So if I want to see the data traffic between the client and the rest of the system, in order to debug it, for example, I have to do something special to make sure that that traffic becomes visible to me. Okay, Wireshark, getting back to the top of this one, Wireshark only can visualize what it sees on the wire. Okay, if it doesn't see it on the wire, it can't show you anything. It does that showing to you by taking the bits and the bits and bytes that are in that message and decoding them and showing you what those values actually mean and interpreting it for you. Usually you're using a PC to capture the data, although some devices such as the Orion have built-in ability to capture data. The Ethernet switches, again, as I said before, can block the uninteresting data to the PC. So for example, either the client talking to the remainder of the system, by default, this switch will make sure that that PC never sees that data. Okay? It's very strange. The purpose of the switch does allow it to forward all of the goose and sampled value data between all the devices, but not the client server data. It's very, very odd. In order to see that, you need to buy a special switch called a managed switch with a mirror port. Now you're thinking that's got to be expensive. Now it turns out Amazon sells these things for $24. They're not expensive. The way you use it is you set it up this way. So you buy this $24 switch plus postage if they charge it to you. You set up one of the ports as what they call the mirror ports, and you tell it that mirror port is supposed to get any data that goes from the client, from this port, from that port, from that port. All of that should be sent back to this mirror port, and then the PC can see all of the data. It's very simple to do. If you forget to do that, though, you'll be quite surprised that none of the client server data is being seen by the PC, and only the goose traffic is being seen. So you say the goose traffic's being seen, it must be working. No, it's because you forgot to put in something with a mirror port. By the way, adding this onto here does not affect the rest of the system. So the client can still talk to the remainder of the system. It just also the results of that will also be sent to this mirror port. If the remainder of the system, by the way, is talking to other parts of the remainder of the system, okay, that don't affect anything on this switch, the PC will again not see that. So the PC will only see traffic that the remainder of the system is sending to and from these devices. I think I went too fast. Yes.
Yeah, I wanted to bring up on here as well that there's a lot of us, at least in NovaTech sales engineering, and I know a lot of you on the line might have a network tap. That's another really useful device if you don't want to do a switch. And dual com makes a very good, very small USB powered 4-port or 5-port network tap that will do kind of the same thing. So something useful for everybody to realize out there.
$24?
No, not that cheap. No, but much smaller.
I see.
Smaller than a deck of cards. So
I see. Okay.
Very easy for troubleshooting if you're out in the field and you don't want to carry a whole switch. But anyway, yep.
There's multiple ways to do it. Yes.
Yeah, exactly.
All right. So let's do a quick visual on what you'd see if you did a Wireshark inspection of some traffic. In this particular example, I'm doing client server traffic. So I've got a device at 192.168.0.33, which is the client, and he's reading a value. The device at 192.168.0.51 is the server, and he's responding to that read request. You can see that the response happens, it looks like it's 4 milliseconds later. It doesn't take very long to make these responses. So what does the client request? Well, I decoded frame 31. simplified it a bit, by the way, to remove some of the fluff. And I'm finding out that it's looking for this thing called domain name of this and an item name of this. You're going to say to yourself, what the heck is domain and item name? Well, domain name is MMS speak for logical device. Item name is MMS speak for data object inside of a logical node. So it's looking at a logical device named GPAM 3000 FCTL. The logical node is CSWI1. The data object that it's looking at is this POS, and it's actually looking for a part. POS is a CDC called DPC, and inside of the CDC DPC, it's looking at the STVal value. What is this supposed to be? Well, it's the position of the switch. Okay, in 61850, switch positions aren't on and off. They're actually double bit values. They're on or off or transitioning between on and off or broken. If you find the value 0, 1, that says the value is off or tripped. A value of 1, 0 means it's on or closed. A value of 0, 0 means that the breaker is currently transitioning between the two. Isn't tripped, isn't closed, it's somewhere between. And if the value is 1, 1, it's broken. So the response that comes back from the server is in frame 33, and it says it's a bit string, and it shows you 2 bits, a 0 and a 1. How did it do that? Well, inside of the frame, actually at offset 50 hex or 80 decimal, it looks like 50, 51, 52, 53. At offset 54 hex or 84 decimal, we have 4 bytes, 84, 02, 06, 40. I want to go through this slowly so you understand what's happening here. So 84 says that I'm sending a bit string, something long, something not a true or false thing, not an integer value thing, not a string value thing, but a bit string. In other words, a multiple number of bits. So that's the 84. The 02 says the number of bytes that follow that, which will be that bit string, is 2. So that's how I was able to group that 06 and 40 together, because the 2 bytes that follow that is this thing in the bit string. The 06 part of this tells me that 6 bits are unused, and the 40 is the actual value. In 61850 land, very odd, sorry about this, it reads left to right and not right to left. So what you'll find that if you convert this 40 hex into binary, it's 01000000. So this 01 that you see here in the blue box is this 01 that was represented by Wireshark. So it did that decode for you. So in the red you'll see the actual transaction. The client said, "What's the value of the switch position?" And it responded, "The value of the switch position is open." It's not closed. It's not halfway between open and closed. It's open now. It's completely open. In that case, you can look for things like look for current going through the switch. If you see any current at all going through the switch, you can tell that switch is now having a real problem, because you've tried to open the switch and yet it's still conducting current. That'd be very bad. Okay, so if the switch is open, you can pretty much be guaranteed that 0 current is going to be flowing, or like I say, or something really bad has happened. So let's go through a bit more detail here. What is actually going on inside of that 84020640? This is what's called the basic encoding rules of abstract syntax notation 1. And I'm sorry if it's getting a little complicated, but in that we have the tag length value. I did describe that. So the tag says what it is. In our case, tag was saying bit string 84. The length here was telling you the number of bytes after the number of bytes in the value. In this case, it was 2. And the value here is 0640. The value it's actually recursive. The value actually consists of another tag length value, for example, inside of that. The value could also consist of a series of tag length values. So it could have tag length value, tag length value, tag length value, or the value inside of one of these could be itself another tag length value. So this is how you structure data inside of the data that's being sent across the wire. All of it is self-describing, so I can see based on the length what this stuff is. So I can see that I've got an 0640 coming up. Because I knew that it was a bit string, I know that the first part of this is the number of unused bits, and the 40 is the number of 40 is the value. So when I decode this, because I know I've got 6 unused bits, I take the left 2 bits, which is what's left over, and I know the rest of this is just junk. So the value is 01 XXXXX. There's the 6 X's here. To get the count of bits, there's a simple algorithm. You take the length here, multiply by 8, subtract 8, and then subtract the number of unused bits. So if you run that calculation, you'll find it's 2 times 8 minus 6 gives you the value of 2. That's how I know there were 2 bits being sent, and that's how Wireshark figured out to show you 01. This is actually what Wireshark shows you, 01. So it does all those calculations and makes all that for you. Sometimes Wireshark lies to you, and the reason is that sometimes Wireshark isn't sure about signed versus unsigned data. If you're looking at something and it doesn't seem to make any sense, try adding a signed value of 256 or 65,536 and see if that makes sense. For example, sometimes you'll see that a value of 127 when it increments becomes a minus 128. You'll say to yourself, that doesn't make any sense. Take the minus 128, add on 256, and see if that makes more sense. When you do that, you'll find out the value is plus 128. Aha, it incremented from 127 to 128. Now it makes sense. Wireshark just got confused and thought that incrementing 127 to a value of 100,000 meant it was a negative number. So sometimes you just have to do a mental calculation. The other odd thing in 61850 is the bits are backwards. So 01. So the Mosimian bit of a bit string is the data value. Another odd thing in 61850 is the Booleans, the true-false values. In 61850, in basic encoding rules in general, a true is anything but 0, and a false is 0. So it's kind of different than other ones. Whereas in many other protocols, a true is a 1, or it's a byte of all ones. In 61850, it's a non-zero, which sometimes confuses people because some devices will report non-zero values. And I believe that's the end of it. So now we're up to the question and answer portion. And I know I've gone very fast, but are there any questions that I can answer at this point?
You answered a couple of them. I've answered a few that were pretty straightforward. There is one here. Does IEC 62850 need a specialized switch to work properly?
That's an interesting question. In general, no. If you're using precision time protocol, yes. And what's needed for precision time protocol is something called a transparent clock. Now, there are many switches out there that will operate as a transparent clock. That's not really all that special. It's not really specialized for 61850. It's specialized for precision time protocol. So any precision time protocol Ethernet switch is going to be suitable for 61850. And if you're not using precision time protocol, any switch will be suitable for 61850. You don't need to have these special switches that I've defined. You don't need to have one of these for an operational system. This is only needed if you want to do debugging.
Awesome. Perfect. Yep. Yeah. Another question is, how does 61850 interface with other software like asset management software? Is it, have you dealt with that where they would transfer data? Is it just transferring logs or reports to other software? Or?
I honestly don't know how it works. I assume it works similarly to how the Orion works, where it takes the data and puts it into some database, and then from there formats it to the required destination format. Maybe it's Excel, maybe it's who knows.
Yeah, that's kind of what I would.
Yeah, it doesn't. There's no real simple one answer to how 61850 interfaces to everything else. Typically, right, you will have a 61850 interface built into your asset management system, and the asset management system will request the data that it needs, however it does it.
Right. Perfect. That's what I would have expected, but I wasn't sure either. So
that's fine.
Will PRP affect debugging using Wireshark?
No, in fact, parallel redundancy protocol is quite interesting in that it fully operates with only one of the links connected. What happens with the second link only becomes relevant if the first link dies. So if you have if you hook up to either the primary or to the secondary link, and they're known as A and B in the parallel redundancy protocol, either one will give you the same information on Wireshark.
Perfect.
Is that it?
Yep.
Okay.
Yep. That answers it. That is all the questions.
Okay. We need more questions.
yeah. If there's any others, anything on IEC 61850 or anything at all at this point, if you have another question, we've got a few people on that can answer those. Let's see. Oh, here we go. Here's one. Are there any issues with having DNP traffic and 61850 traffic on the same LAN? Is it best practice to put them on separate VLANs?
There is absolutely no interference between 61850 and DNP. And the reason is because, let's go back and show you that. It has to do with all of this addressing. In 61850, we'll have a TCP port number of 102, and DNP will have a port number of 20,000. So so this gets pushed up to the MMS stack if it's 102. If it's 20,000, it goes from the DNP into a DNP stack. So the two things are completely ignorant of each other and operate in parallel without any problem at all. You do not need to run multiple virtual LANs.
Perfect.
Not needed at all. In fact, the same is also true for Modbus. Modbus uses port 502 in TCP. And I had a question many years ago, does Modbus and DNP interoperate with each other? And the answer is yes. They just happen to share a wire. But at the TCP level, they're different port numbers. And once they're different port numbers, they're completely independent of each other. In fact, they won't even see the other traffic.
Yep, exactly. Perfect. Thank you. One more question. When reading 61850 enabled devices, we're having issues with responses that don't come in for 1 to 2 seconds. Is there a way to speed up 61850? Is it based on what the server allows?
Okay, I will tell you what's going on, because that same issue drove me crazy for the longest time. It's the client that's not asking the question. The client that's asking the questions every couple of seconds. It's not the server delaying its response. It's the client delaying its request. So you simply have to go into the client and make the request more often. As you see in my example here, and this is not a high-speed system. The server responses are generally in a small number of milliseconds. If you're seeing anything but a small number of milliseconds, in other words, something you can't see, then something is really wrong. It's completely broken. So 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 the actual answer is you're seeing the client only making a request every couple of seconds. And I can mention by name clients that do that by default. In fact, one of the clients, and I don't want to mention the name, by default polls every 5 seconds. And it's a very simple matter to tell it to change that polling interval down to 1 second. And if you operate that particular client using an Excel-based application, you can get that time down to milliseconds.
Perfect.
So if the name of the client begins with an S, you have the answer.
Great. Let's see.
You'll know your client.
Yeah. What we have here is 61850 localized to communication between substation devices, or does it involve comms to the data center EMS? Will that require a rebuild from DNP?
Generally, the way it's done, let me just say that there are not that many EMS systems that natively speak 61850. There are a couple, but most of them will be speaking DNP. And what's typically done is that you do a 61850 to DNP translation at the substation and talk DNP back to the control center.
So that's what I've seen mostly too.
So typically what you do is you have a 61850 substation in general. You convert that to DNP using a gateway such as an Orion, and then you use that and you talk back to your control center using DNP. Now eventually the control centers are going to upgrade to 61850, and that becomes a very simple matter of just essentially removing the gateway, or removing the functionality of the gateway and just leaving the controlling ability in the substation controller there. But you can remove the gateway requirements.
Perfect.
Unfortunately, if you convert 61850 into DNP, you're then left with all these addressing problems where you have to make sure that you don't have that your addresses don't collide. So that's where so you have to go. So you're back in that arena. If you stick with all 61850, the names of the objects can stay all the way back to the control centers.
Let's see.
Without change.
Do sample values cause bandwidth issues with normal Ethernet traffic?
Yes.
I figured that was the answer, but
oh, it's very simple. So if you multiply it out, it's not magic. Take 4,800 samples per second, and then multiply that out by eight samples that are in there. So we have 4 volts and 4 amps. Each of them being transmitted as 32 bits. Each of them also has a quality transmitted as 32 bits and 4,800 times per second, and you multiply it out and you find out it's 6 megabits per second. Low-speed Ethernet channels used to be at 10 megabits per second. That's a good chunk of the 10 megabits. Is it still? Are you allowed to? Are you going to be happy having one of those links and 61850 on the same link? Yes, that will fit on one 10 megabit link. If you want to have more than that, though, you've got to go to a 100 megabit link. Now, 100 megabit is these days that's almost what everybody uses. So you can put about 6 or 7 or 8 of those merging units on a single 100 megabit link and not have a problem. 61850 is not bandwidth hungry. Regardless of what you hear, it's not bandwidth hungry at all, because most of the data transfer in 61850 again is all pushed data. You don't actually clog the network up by saying what's the data right now, what's the data right now, what's the data right now. That's not how you operate 61850. So it's a generally low amount of data transfer. So moving along, people are now moving from the 100 meg links into 1 gigabit links, and 1 gigabit link lets you have even more of these without interfering. Typically, you can easily load a network up to about 50% of the network of the capacity of the cable without running into problems. So just a back of the envelope calculation, let's go 100 meg link. You load it down to half. Half of that would be 50. 50 divided by the 6 megabit, that gives you about 8 or so. So on a 100 megabit link, you can easily accommodate 8 of those merging units that I've just described. Again, that's a back of the envelope calculation. Your mileage may vary.
Perfect. And we do have a couple more questions, but I know we're now past the 2-hour point, so we'll go ahead and close out. But all the questions, again, like we mentioned at the beginning, we will provide all the questions with all the correct answers, intelligent answers, as Bruce said, or as intelligent as we can do, to you all at with the follow-up email. Again, that usually comes out about a week or so after this, so look for it sometime, I'd say mid to late next week. This one maybe take a little longer. We do have quite a few questions, and that takes us a little time to make sure we get really nice answers for you. The Power Support Community, if you have not registered for that, please do. This is our new community, new support site for everything NovaTech Power. So software, documentation, application notes, all the videos from all the different webinars that we've given for the last year, a little over a year now, are all there. Lots and lots of information. This is for anything NovaTech Power. So Orion, Bytronics, you name it, it's all located here. It's power.novatechautomation.com. You register. It is a manual process for us to approve those registration requests. So it does sometimes take a little while. So if you don't get an immediate response, don't worry. We have gotten your request, and we will get to it. It just takes a little bit of time. If you want to schedule a session with one of our sales engineers, you can see that right here. It's now there's a new link. Sorry, Bruce, I forgot to give you the new address, but it is very easy for everybody. It's booking.novatechautomation.com. So nice and simple. That will take you to a booking site that will allow you to book time with one of our sales engineers. And you can see kind of the example of that here. And allows you to pick a time that's easy for you, and then you can see who's available and pick that time, and then they will set up a session with you and help you with whatever you need help with. I believe that is, we have one more slide, or nope, that's the end. All right, perfect. Thank you, Bruce. We appreciate all your time and your prep for this. It was an excellent session.
Thank you. And I want to invite everyone to download the slides when they get a chance, and to go through them on your own, because there's a lot of good information that is built into those slides. I spent quite a bit of time making those, and there's some really good stuff there that I didn't cover in its entirety because it's just too much to pack into 2 hours, and I didn't want you to go to sleep.
Perfect. And we will,
yes.
Yeah, we'll make sure we send the slide deck out to everybody with that follow-up email, and then we'll make sure it's posted on the new support site as well. So with that said, I want to thank you all again for attending today. I know it's a long one, but I appreciate everybody sticking with us through it, and hope you got a good amount of information out of it. If you have questions, comments, please feel free to reach out to Bruce or myself or anybody at NovaTech, and we'll help you out any way we can. Look forward to seeing you guys in 2 weeks. We'll have one more webinar on the Orion I/O, so look for that registration announcement coming out, and we will see you then. Thank you very much.